All right, so I want to do an example problem. Basically, with it involves dielectric. So I have a parallel plate capacitor, and I charge it up to some total charge Q naught, or we can call it Q total. The battery is removed, and then from the left I insert a dielectric such that it takes up half the volume of the capacitor. And what I want to do is I want to talk about the total capacitance of the system, the electric field, the electric potential difference, and the charge density. And so I'm going to go through all the details of this calculation in this video, which I don't go through during the class because it can be quite a long problem. Okay, so here I've drawn the capacitor. There's no dielectric here, so kappa is 1. So the capacitance of this device is epsilon naught A over D, as we know. The charge density is Q total over A. So just for simplicity, I can make this the top positive and the bottom negative. And the electric field in between the plates is the charge density divided by epsilon naught, the surface charge density on the plates divided by epsilon naught. And I can also write down the total energy stored in between the plates by this expression, which is Q squared over 2C. So what happens when I insert the dielectric in between the plates? And this dielectric only takes up half the volume. Of course, if it took up the entire volume, the capacitance would increase by a factor kappa, but that's not what happens here. I have half the volume that this thing covers. Well, what do I know? Well, when I put this in, what's going to happen in the dielectric is that you're going to create a dipole field within the dielectric that's going to try to want to cancel out the field due to the charges. What's going to happen is the charge distribution on the plates is going to change. In fact, the total charge on the left-hand side here is going to be different than the total charge on the right-hand side. But since the charge can't go anywhere, we can say that Q total is equal to Q left plus Q right. And I'm just going to use L for left and R for right from now on. So I'll write it this way. We can also say something about the charge density. We can say that the charge density on the left is going to be equal to Q left over A over 2. And sigma right is going to be Q right over A over 2. Because this takes up half the area of the plates. What else can we say? Well, what can we say about the electric field? Here and here, what can we say about the electric field on both sides? And that's an important question. I think it should be obvious, since these plates are big, the field here and the field here, whatever the value is here, or whatever the value is here, is uniform because of the size of the plates. We're assuming that the plate separation is small compared to the dimensions of the plate. Okay, well, if that's the case, then if we have a uniform field, then what about the equipotentials? What about if I march across here and I just draw that equipotential line? Now, is the equipotential the same value all the way across from this side of the boundary to that side of the boundary? The answer is yes. These equipotential line, the value of V for that equipotential and the value of V for this equipotential, they have to match because at the boundary, V has to be continuous. And we can do this all the way across. If you look at this equipotential line, the V here and the V here have to be the same. So what that means then is the potential difference on the left-hand side is equal to the potential difference on the right-hand side. And we'll call it just delta V. And so that means the electric field on the left has to be equal to the electric field on the right. Because otherwise you're going to have a discontinuity in V here. And that's something that's not physical. So what does this mean that the potential on the left equals the potential on the right? So the delta V here and the delta V here are the same. Well, what this means is that you have two capacitors that are in parallel. That's how you would treat it. So treat it as two capacitors. In parallel. So, what is the capacitance on the left? What is C left? Well, it's going to be kappa epsilon naught half the area over D. Where D is, and I forgot to mention, D is the plate separation. C right is going to be epsilon naught A over 2, the whole thing divided by D. What's the total capacitance for the system? Well, they're in parallel, so my total capacitance is going to be this capacitance plus that capacitance. So when I add the two together, when I add these two together, and this is going to be a fairly straightforward calculation, I'm going to get epsilon naught A over 2D times kappa plus 1. That's my total capacitance for the system, which is going to be equal to, well, you can write it as Q total over delta V. That delta V has got to be equal to these delta V's. So delta V then is going to be what? Delta V is going to be Q total divided by this thing. So that's delta V. Now I can actually figure out what the charge on the left is and what the charge on the right is. I can figure out Q left and I can figure out Q right. Because Q left is going to be C left times this thing. And C left is this expression. You can see this is getting messy here. All right, so Q left ends up being Q total times kappa over kappa plus 1. What about Q right? Well, Q right, the Q on the right, let's Give me a second, I'm going to have to adjust my camera. So Q right is going to be C right delta V. And when you do this, the math, you get Q total over kappa plus 1. And if you add this to this, you will get Q total. Now, what's sigma? What's the charge density? So I'm going to actually come back here. Sigma left is going to be this divided by the area, okay? Times A over 2, or I'm sorry, divided by A over 2. I can write it this way. Where sigma is this guy. Similarly, sigma right, I can show sigma right ends up being 2 sigma over kappa plus 1. Okay, now what about the electric field on the left and the electric field on the right? E left is going to be sigma over epsilon, where this is kappa over epsilon naught. This is sigma left, sorry. So it's going to be this term and that's going to give me 2 sigma over kappa plus 1. That's the electric field on the left. Now the electric field on the right is going to be this over epsilon naught. And so E right is 2 sigma over kappa plus 1. The field on the left and the field on the right are equal. But then what about this 2? Well, where does 2 come from? Well, that's because this thing rearranged the charge in my system. Okay? But if kappa is 1, if I change this to basically a dielectric, that's kappa equals 1, basically a vacuum, then I get 2 over 2 equals 1, and I get, oops, I forgot my epsilon naught here. I get cancellations to occur, and I get the same field. Okay? Let's pause for a moment. Okay, so what I want to do now is I actually want to look at what happens if I just, instead of putting it halfway in, I'm going to put the dielectric a certain distance x into the plate. So let me redraw my picture. And I want to keep the purple equations. And I'm going to get rid of all this. Let's say I have the device not connected, and I'm going to shove a dielectric in. And that I haven't shoved it in all the way. I shoved it in at distance x, and then this is L minus x. Okay, I shoved it in at distance x, I haven't shoved it in all the way. I want to write the energy stored in the capacitor as a function of that X. Okay, I want to write the energy stored. So basically, I can draw that picture here again. I can call this X. And this distance L minus X. I want to look at the energy stored in this thing. Now, as I'm shoving the dielectric in between the plates, oops, that's a mistake. As I'm shoving the dielectric in, the total charge on the plate stays the same. The voltage does change, but the charge stays the same. And so I want to write my expression for U in the following manner. I'm going to write U this way. I'm going to write it in terms of the total charge on the plates and C. So the total energy is going to be written Q squared over 2C. Because the Q doesn't change, the C will change. I don't want to write it in terms of V because then I have to derive an equation for V as a function of X, and that might take a little bit of work. It turns out by me doing it this way, it's going to be a little bit easier. I need to write an expression for C because the numerator is the same. I want to know the total capacitance. That's going to be C left plus C right. Well, C left is going to be epsilon naught A over D times whatever fraction of the area this is in underneath. So I'm going to put A X over L. So if X is 0, then none of it's in the plate. If X is L, then the entire thing is shoved in. And then I got to put a kappa here because this is the dielectric. The other side has no dielectric, and what's left over is L minus X. I'll write it like this. So if X is L over 2, for example, then I'll get A over 2 here and A over 2 here. So let me combine terms and rewrite this. So I'm going to get epsilon naught A over L D. And then in the brackets, I'm going to have X plus, or kappa X plus L minus X. I can rewrite it in the following way. So that's my total capacitance. So now my total energy is going to be Q squared divided by this thing. So U is going to be Q total squared over 2 times 1 over this. I want to know, what is the force on that dielectric? What is the force due to the field? You know from physics 205 that du over dx, or minus du over dx, is the force due to the field. So if I take the derivative of that with respect to x, and take the negative of it, I will get the force due to the field. So F is going to be the negative of du over dx. So what is that going to give me? I got to take the derivative of this with respect to x. So first of all, that's going to raise the, I'm going to get a minus sign out here. And then there's another minus sign here, so that's going to cancel. I'm going to get L plus x times kappa minus 1 to the minus 2. Then the derivative of the inside function, kappa minus 1. Now, epsilon naught a over d is just 1 over c, the original c. Maybe I should call this, I should call it c naught, the original capacitance. So then I'm going to get Q total squared over 2c times kappa minus 1 times L plus x times kappa minus 1 minus 2. Of course, that's my initial energy. So that's the force due to the field. It's positive. It's to the right. So the field's sucking in the dielectric. Okay? The force I have to apply to make it go in at constant speed is in the opposite direction. So the field's sucking in the dielectric. And the reason why is because when you're inserting this, the field lines at the border will actually start to bend, and that bending of the fields causes that force on the dielectric.